So please join me in welcoming Dani DellaGiustina.
Thanks, Carmi. Okay. So today I'm going to be telling you all about the Osiris-Rex mission, which, as Carmi introduced, is an asteroid sample return mission. This is an artist's conception of what it looked like during the sampling phase. And I could literally spend hours talking about the incredible science that we've been able to accomplish by sending this spacecraft to a small asteroid that is very near to Earth in the solar system. Its path actually crosses the path of our own planet, so it's also hazardous. But one thing I would like to focus on that I feel like is underserved in a lot of scientific talks is the human component. Because at the core, all of these NASA missions and all of the incredible technology that we're constantly developing and accelerating, these are human endeavors. And so I'll be spending quite a bit of time talking about how we not just built a spacecraft and some instruments to sample an asteroid, but how we built a team and what are some of the core design principles when it comes to putting together a team that can enable success in the face of pretty incredible challenges. All right, but to start, I just want to paint a picture of how much planetary exploration we have done as a species, really only in the past 50 years or so. So what you can see here is planet Earth, and there's these traces that are emanating from our home, going all across the solar system. Each one of these lines represents a planetary exploration mission that has been conducted. So you can see there's a lot of exploring that we've done in the inner solar system. These are our neighbors, the Moon, Mars, Venus. And then as we get into the outer solar system, there's far fewer paths that have been traced. We haven't done quite as much exploration in the outer solar system, but we have done a little bit. So there's been about 200 planetary exploration spacecraft that have been launched, and of these 200, only 9 have been sample return missions. So sample return means that we go to another planetary object and we take a little piece of it back, bring it back to Earth for further study. And this is a really incredible frontier within planetary exploration because we can basically get tenfold the scientific return by examining a piece of a planet on Earth in giant facilities versus what we learned from spacecraft. Of the 9 sample return missions that have been conducted, 3 have been to asteroids. And you might be asking why. Why have we sent so many sample return missions to asteroids? Why should we care? Asteroids are pretty fundamental in terms of understanding both our past in the solar system as well as our future. And so by studying them, we can answer some pretty big questions, like where did we come from? How did we get here? And what is our future? What is our destiny? And the reason for that is that these objects are really the remnants of solar system formation. So really early on in our solar system's history, before all the planets formed, there was a lot of gas and dust swirling around our sun. And some of this gas and dust clumped together as it was rotating, pulled by the sun's gravity, and they started aggregating into little pieces. These little pieces eventually coalesced into little planets, what we would call planetesimals, and those are essentially the building blocks of the planets. So many asteroids represent these remnants, these sort of ancient relics of solar system formation. We have a number of meteorites on Earth that come from asteroids, and these span a range of different compositions and types. They contain a lot of different minerals, and some of these are full of carbon, full of hydrated minerals, with a water signature that is very close to the water signatures that we see in our own oceans. And so we know that asteroids might have delivered the precursors to life on Earth. So again, kind of helps answer this question of where did we come from? On the flip side, we also know that asteroids have been responsible for some major extinction events in Earth's history. So early on, this is kind of a zoomed in view of that swirling disk of gas and dust around the sun. As those asteroids, those planetesimals were accreting, they also frequently impacted our planet and really all the rocky objects, all the objects in the solar system. And we see the remnants of these impacts in craters on Earth and especially on other surfaces of planets without atmospheres. And we also have a lot of evidence to suggest that the extinction event that led to the die-off of the dinosaurs about 60 million years ago was caused by a major impact that was the result of an asteroid hitting the Earth somewhere around the Yucatan. There is also, as I mentioned earlier, a number of objects that currently exist in our present-day solar system whose path crosses the path of Earth. And so there's quite a bit of investment from NASA and government agencies around the world to try and find all the near-Earth asteroids so that we can potentially plan for any sort of hazardous impact in the future. And lastly, asteroids hold a lot of potential for resource extraction and utilization. So many asteroids are rich in rare earth metals, in precious metals, in hydrocarbons. I think a lot of the other talks that we've heard today have focused on sustainability and the fact that we're growing as a species, and at some point in the future, we may not be able to sustain ourselves if we keep consuming our own planet. But asteroids might help answer this question in the future. I don't know how many of y'all have seen The Expanse, but when I would talk about this 15 years ago, I felt like a lot of people thought it was so far off in the future. At this stage, the idea that we might be able to use asteroids for resource extraction, I think, has begun to pervade some of our societal consciousness as a possibility. All right, so I've hopefully convinced you all that asteroids are pretty worthwhile objects to study. We can learn a lot about them, a lot from studying them. And next I'm going to talk a little bit about Osiris-Rex, which is this spacecraft that we built in order to study an asteroid named Bennu. Bennu was an object of a lot of interest because some of our earliest data, when we were looking at it from telescopes, it just looked like a point of light, indicated that it was one of these asteroids that was dark, so it probably had a lot of carbon. It was about the same brightness as coal. And so it might represent one of these objects that could have delivered precursors to life on on the early Earth. So the Osiris-Rex spacecraft, you can see there's this big disk in the center of what is our science deck. This is basically one side of a cube, and this cube is about the size of a RAV4, so it's not a very big object. And then there is this arm that's stretched out. That was our sampling arm, and at the end of our sampling arm was a device that you can see right here, which was the mechanism developed to collect a sample. This basically works by slowly touching down on the asteroid with that arm stretched out, and right when we touch down, some gas is released. It entrains grains of material from the surface of the asteroid into that device. And what I want to point out here is that the slot that the sample would go into is only about 3 centimeters wide. So we were counting on having material that could fit into that 3 centimeter slot. 3 centimeters, to give you a sense, is about the diameter of a quarter. So we're looking for pebbles, material that's about the size of a quarter. We also imaged the asteroid quite a bit using 3 cameras that were developed at the University of Arizona, and I'll be showing you some fantastic images from those cameras later today. We had 2 instruments on there called spectrometers, which were more or less able to look at the surface of this asteroid in wavelengths of light that we can't see with our human eye, and also with a lot further discrimination between colors in the wavelengths that we can see with our human eye. One of these spectrometers looked at thermal wavelengths, called a thermal emission spectrometer, but all you need to know about that is it can basically tell you how hot the surface of this little asteroid is. How is it heating up and cooling down? And then we had a laser altimeter on the mission. This just basically could tell you how far you are from the surface of the asteroid based on laser light traveling back and forth. So why did we design a spacecraft to look like this? We had some preconceived notions of what Bennu would look like before we arrived at it, and these expectations were driven by a lot of evidence, but what you'll come to find out soon is that they were mostly wrong. So some of the evidence that we had that contributed to our design of this spacecraft and these various instruments came from other asteroids that we've visited in the past. So this is an image of asteroid Itokawa. It was visited by a Japanese mission called Hayabusa in 2005. It's about as long as the Empire State Building is tall, and what you can see is that even though it's this rocky rubble pile world, it has this sort of pond of really fine-grained material towards the center. Everything that we had seen in terms of other asteroids prior to Osiris-Rex going to Bennu looks something like this. So we had this idea that there should be a lot of areas of fine-grained material, or at least some giant ponds of fine-grained material. And that's why we designed that sampling mechanism that I showed you that can collect quarter-sized pebbles or smaller. Another important thing that we did before we built the spacecraft and we went to Bennu is we studied it with some telescopes on Earth. One of these telescopes that looked at thermal wavelengths indicated that Bennu had something called a low thermal inertia. So thermal inertia is a pretty technical term, but I guarantee all of you understand what thermal inertia is. It's basically, if you've ever been to the beach and you're there in the morning, the sand is very cold, and then as the sun rises, you're in the heat of the day, the sand gets very hot. And then at the end of the day, it cools down again really quickly after sunset. So we would say that that ability to heat up and cool down really quickly is called a low thermal inertia. And the opposite would be a big boulder, right? A big boulder in the morning, sitting in the sun, it might take a while to heat up, and at the end of the day, that heat is going to slowly radiate away. It would have a high thermal inertia. So when we looked at Bennu with these Earth-based telescopes that could see how warm it was as a function of its 4-hour day, it has a 4-hour day, so it rotates once every 4 hours, those data indicated this object has a low thermal inertia. It probably has a surface that's pretty sandy. And that's what we were expecting when we met Bennu. But as you can see, we were not right. Bennu did not have a big pile of sand on its surface. In fact, it really didn't have very much sand at all. It had a lot of boulders. And so Bennu is about as tall as the Empire State Building, a little taller. And those boulders that you see, if you can see them with your naked eye at this scale, they're the size of buildings that are a couple stories tall. So think about, the buildings around downtown Austin here. And this really led us to two fundamental questions that we had to ask ourselves. We've designed a mission that maybe wasn't for this type of asteroid. How are we going to get a sample? Where is our device going to find material it can collect? And then how are we going to take our SUV-sized spacecraft down to the surface of basically a city block, right? How are we going to thread the needle to navigate down to the surface and get a sample? So how do we get there? Where are we going? And the way we were able to adapt to reality and compensate for the fact that maybe we did not have the ideal tech was to put together a team which really proceeded and went hand in hand with developing our technology and our hardware that was able to weather challenges and meet them with success. So what I'm going to be talking about for most of my time here is what are the design principles that we had that saved the day. The first one is something called traceability. And traceability is this systems engineering term that basically means every single decision and choice that we make is motivated and can be linked back to our primary goal. In this case, we're an asteroid sample return mission. Our primary goal is to collect a piece of asteroid Bennu and bring it back home. And that means that we made very few arbitrary choices and that we had a lot of clarity whenever we had to make a decision because we could quickly evaluate, how does this get us back to our primary goal? The next major design principle that helped us save the day was redundancy. And what this means is we always had a plan B. Another way to say this would be that we tried to minimize single point failures. And so this pervaded almost every aspect of our mission. On those instruments that I showed you on the spacecraft, they all had redundant electronics. So we had electronics, basically 2 sets of electronics for every instrument in case a solar storm or a cosmic ray came, took out a component on one, we could flip to the other side. Also in our team structure and our team hierarchy, we had leads, and they always had to have a deputy that they could delegate things to or could make a decision in their place. We had redundancy built in across every level, hardware, software, human. The next major design principle that really helped us was flexibility, which meant we could bend without breaking. We could kind of roll with challenges because we had built some margins, some slack into all sorts of elements across the mission. One example is we had a very detailed schedule, getting back to that traceability principle, because every day, every hour that we allocated for using the spacecraft, we had to convince ourselves it traced back to that goal of collecting a sample. But then we specifically just scheduled dead time at various points when we knew we were going to have some decision making to do. We had flexibility to rethink, to reflect, and to redesign if we had to. And finally, we had buy-in from everybody on our team that the earlier design principles were important and that they were what we would enact across all of our future decisions. So we had buy-in, and this really gave us a lot of clarity whenever we faced a difficult situation. The team could kind of collectively get together because we were all on the same page about the priorities and how to respond to them. We also had a really transparent work culture. All right, so now getting back to that first question of where do we go? This is the surface of Bennu, and so we saw it rotating earlier. This is just in a 2D map view, and you can see it still looks pretty rocky, and it still looks like we're going to have a hard time finding a sandy beach to collect a sample from. What you can see here in these boxes are different boulders. So remember we talked about this concept of thermal inertia earlier. Well, when we made a map of thermal inertia using one of our instruments of the spacecraft, where the warmer colors signify high and the cooler colors signify low, you can see that all of those boulders that I had highlighted had a low thermal inertia. So this is really confusing to us because it meant that the way that materials behave on this small asteroid is not the same as we would expect based on our experiences on Earth. And we simply could not use this data any longer to answer the question of where do we go. So what did we do? Well, we had to be traceable. So our plan had to meet our goal, and that meant that our plan of using thermal inertia to find sandy spots on the asteroid, it was out. We needed to pivot, and we needed to identify a new mission plan. And you can imagine this was pretty hard because we had invested literally years into developing a plan that we thought would close and get us to the surface of Bennu. But we had, it no longer allowed us to meet our goal, so we had to revise. We were able, fortunately, to revise because we had redundant capabilities, meaning that we had another way to look for that sandy material. We had included 3 cameras on the spacecraft. And so instead of relying on this thermal inertia data, we were going to instead rely on images. Now, our plan did not initially include the ability to image the surface at the level of detail needed to identify quarter-sized pebbles, so we had to replan. And we were able to do that because we were flexible. So I had mentioned earlier that in our schedule, we had these points of basically slack or dead time. And we were able to reallocate that margin, that slack, in order to collect more images, which was important because this came up a lot. Finally, for getting to an asteroid, realizing you designed the wrong spacecraft to get a sample from it, our team actually responded to this challenge with a lot of positivity. People were almost excited that there was this challenge that we had, and were really interested in developing the creative solution needed to overcome it. And we were able to do that in a constructive way without making anybody feel like there was a loss, that their instrument or their plans were not going to get used, because we all bought in to the 3 prior principles. We all knew that our plan had to meet our goal. And the end result of all of that is we found what was the most relatively boulder-free area on the asteroid after several re-imaging campaigns, which you can see right here. There's still a lot of boulders, and for scale is a silhouette of our spacecraft. But this was the most boulder-free area, the area most likely to have sandy material on the surface of Bennu. So then we had to figure out, how are we going to get there? As I mentioned earlier, with boulders this size and this small spacecraft, we really would need to thread a needle to get down to the surface. And that meant we had to refactor our plans for spacecraft navigation. So here is how we enacted those design principles yet again in order to achieve our goal. So traceability, we knew we had to go down to the surface, right, to get the sample, but we had to do it safely, because there is no sample return mission if you crash your spacecraft. This was going to be really challenging because our original navigation system was designed to touch down within an area that's outlined by this orange circle on this, relative to this image. And so that means that it was only accurate enough to get you anywhere within that circle, that orange circle, but you couldn't precisely choose where. And we needed to land in that blue circle somewhere. That's where the sandy material was. We didn't want to accidentally ram into the side of one of these big boulders that's the size of, a skyscraper across the street. And so we assessed that we would have to redevelop our navigation system. Fortunately, we were redundant. Very early on in the mission, we had realized that our primary way of navigating to the surface using a laser that basically shot distances back and forth, it was potentially a single point failure if one of those lasers failed. So we had developed a backup capability to use something called terrain relative navigation. And all that means is that you have a smart system on your spacecraft that can look at images as you're taking them and compare it to a predefined map and kind of figure out where you are based on those images. And so even though this was not our plan A, our plan A became, our plan B became our plan A. And we turned around and decided we were going to use this different system and collect more images so that we could get to the surface. To give you a sense of how challenging this is a parking lot, modern day parking lot based on what we typically use in the US. And so the size of the circle that we needed to land within to collect material was just a few parking lot spaces. This is an example of a boulder like the one that you can see at 4 o'clock. And so if we accidentally backed into it as we were leaving post-sample collection, or we hit the side of it, we would be toast. And so we had a big challenge in terms of reducing this orange circle to the blue circle with our navigation technique. Again, we had a lot of flexibility in our schedule because we had thoughtfully inserted that margin, that kind of time allocated for dealing with unforeseen circumstances. And so we used that to collect more images for our new navigation system. And in order to develop this new navigation system, we had to bring a big, diverse team together and unite them across very different disciplines. So the folks that had developed the cameras that were only interested in studying an asteroid as a relic of the early solar system had to explain their data to our spacecraft engineers so they could upload those images and those maps to the spacecraft and use that terrain relative navigation technique. And that was only possible because we had a lot of buy-in on these first 3 principles across all of our different team members. And here is the result of all of that work. So this is that arm stretched out as we are sampling the asteroid, and boom, you can see how much material we kicked up right when we got to the surface. So this is the 2 image frames right at the point where we are collecting a sample. And you can see the surface, the head of our sampling mechanism is moving into the surface a little bit, sinking down, meaning we probably stuffed that sample return capsule full. In fact, we stuffed it so full that when we looked at images after the fact, so this would be that sampling head at the edge of the spacecraft, and we're looking at it with one of our cameras designed specifically to capture these images, we realized that there was so much material it must have been jamming the inner throat of our sampling mechanism, and some of that sample was now leaking into space, which was exciting because it meant we got a ton of sample, and also terrifying because it meant we were leaking sample into space. Some of it was hitting our spacecraft. But we were able to, once again, in the face of this unforeseen circumstance, we were able to apply those 4 design principles and quickly get this thing stowed in that sample return capsule. So the sample is on its way back to Earth in September of 2023, which is a year and a half from now. It'll land in the Utah test range. We'll take apart that sample, the sample return mechanism, and we'll end up studying it for a period of 2 years, and then the sample will be publicly available really to the entire world to apply, to get pieces of and examine in various laboratories. One of the things we're super excited to study with the sample is, does it maybe contain some of the amino acids that might be key in understanding the origin of life on our own planet? And then our spacecraft is going to go on another journey. So it's going to go on a journey to an asteroid called Apophis. This is our current best guess at what Apophis looks like based on radar data. It kind of looks like something that belongs in Minecraft. But I'm pretty sure when we eventually get there, we will be surprised and revise completely our understanding of what this world looks like just based on our experience at Bennu. Every one of these asteroids seems to be pretty unique in some type of unforeseen way. But I'm pretty confident that those design principles that I talked about today are going to help us overcome whatever challenges we encounter when we arrive at this asteroid. And that's it. Thank you. So questions? Yeah, when we sampled to get to the asteroid, we used basically our propulsion system on the spacecraft to match the rotation rate of the asteroid. And when we were basically rotating as fast as it was, that's when we were able to touch down. We did use ultra pure nitrogen gas to kind of spray at the surface in order to collect that sample. Oh no, that's a really good question. So the question is, did those gas jets blow everything away that we were trying to collect? Basically the thrusters on the spacecraft. They actually did blow away some material, not during collection. At collection, we were almost in a free fall. So we weren't using the propulsion system. But when we backed away, so at that point we had already captured the sample, we did make kind of a mess of the surface. And we have some pretty cool videos of it. And that's actually something we plan to do when we arrive at Apophis, because disturbing the surface of these asteroids is super interesting from the perspective of understanding how rigid they are and how we might mitigate one if it was ever on a hazardous collision path with our own planet. And so we do plan on going down to the surface. Since we have that capability with our spacecraft, we're kind of like a hummingbird and making a mess with bursting our thrusters. Great question. Go ahead.
Yeah, how many days before the collection did you guys realize that the surface was not? And was there like a little bit like, oh no,
Yeah, absolutely. So the question is, how long did we have before sampling after we realized that the surface of Bennu was not what we were expecting? And was there a cold sweat in response to that? So we had about a year and a half. And that sounds like a long time, but it actually wasn't, because in order to plan the maneuvers to get down to the surface, we need several weeks of sort of simulation to make sure that they're going to work. And yeah, we were pretty worried because we were essentially throwing away this plan that we had built, and we had created instruments in order to fulfill that plan, and they weren't going to fulfill that plan anymore. So there was a lot of measured concern, and it was really going back to, okay, what is our process? How do we in a thoughtful way enact those principles in order to meet the goal? Do we proceed? And in the end, it seems like we've collected about twice what we were required to collect in terms of what we owe NASA. So we ended up being quite successful. But it was, yeah, there was definitely sleepless nights initially. Yeah, so the question is, are we going to make any improvements to the spacecraft before the next mission based on what we learned and to make it more adaptable? And the answer is yes. So there is a number of procedures when it comes to planning how to take data using one of these spacecraft that are very manually intensive. They require second shift work and a lot of human power. And we're working to automate all of those with flight software so that we would have a lighter human footprint. We won't have people doing second shift work and things like that when we get to Apophis. And the technology is now at the point where we really can automate a lot of things. Wasn't the case about 10 years ago when we were designing the spacecraft. Yeah, that's right. So the question is, when we go to this other asteroid, does this mean we're just dropping off the sample return capsule? We're not landing the landing the spacecraft back on Earth and then relaunching. And that's exactly right. So the sample return capsule can basically be, it's spring-loaded, and there's some pyrotechnics. So we'll get really close to the Earth. We'll go ahead and release it once we're sitting in Earth's gravitational well. And we have planned for it to land in this Air Force test range in the Utah desert. And we've done kind of this whole flow before with 2 previous sample return missions. So we have a lot of confidence that everything should go as planned. Right. Okay, so the question is the movie Don't Look Up. Yeah, I mean, I would say one of my colleagues actually at the University of Arizona, Amy Meinzer, was a science consultant on that movie. So they really did a good job of getting the science right. That is not too different than how it would look if we were to discover an object that was on a collision course with our own planet. One thing to note that is, it's not discussed in a lot of detail in that movie, but these missions like Osiris-Rex that go to asteroids and survey their surfaces really help us build a nice set of characteristics that will be really vital if we ever have to create a mitigation mission to send to some object, either an asteroid or a comet, and basically either knock it off its course or catastrophically destroy it. So even though the science is a big motivator in a lot of the missions that go to these small bodies, this idea of planetary defense is also a really important side benefit. All right, if there's nothing else, thanks again.